to RCast, the official podcast to the RChain Cooperative. RChain is a complete, concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. Beyond our platform, our investment partner, Reflective Ventures, funds organizations that are working within our core mission statement to create a better world by enabling social coordination in robust, secure, and scalable ways. I'm Derek Barris, the Director of Content for RChain. Each week on RCast, I'll be talking with the founders of our portfolio companies, as well as co-op members, staff, and other figures in the RChain ecosystem about the most pressing issues in blockchain today. Please check out rchain.coop to learn more about the platform, our community, validator sale, and information on becoming a member. Bill Moyers once said that a journalist is someone who is able to educate himself in public. I've always appreciated that. There are many things that I've learned over my career in journalism that I never thought I would have explored. One of the more recent disciplines has been neuroscience, where I've focused much of my energy in terms of writing in the past decade or so, and was actually a focus of my last book, which had to do about the neuroscience of exercise and movement. Since joining RChain last August, I've had a deep dive into technology and programming. I've worked in tech before, but never at this level, and I've never been around so many people interested and knowledgeable in math. That is definitely something outside of my range. So I'm not going to comment much on this podcast, but it was fascinating listening to Greg Meredith, who of course is the president of RChain, and Chris Williams, a software engineer who has been involved with RChain for a while now, discuss the row calculi and some of the mechanisms behind it. So I'll leave it at that. Enjoy this conversation. As you will hear, it is sort of a part one. We left off somewhere that Greg will continue, probably with Chris and maybe some others at a future time, probably in the near future, as I think this will be of interest as it has been in the community calls on Wednesdays. Lastly, you'll want to make sure to check out our blog, as there are diagrams that are referenced that you need to see in order to understand some of the points that they're making during this talk. So here you go. Buckle up.
First of all, I want to thank Derek and Christian. Thanks, Derek, for setting this up. We're going to do a little podcast here, I guess, on some design level thinking around computational calculi. And sort of the point of it was to illustrate that the row calculus is sort of not one calculus. It's actually a whole family of calculi. And to begin to give, like in the spring of last year, I gave a short course on an introduction to the design of computational calculi, and there was a lot of background material that the group needed to come up to speed on, so that we couldn't really do design level thinking. I was thinking again about how to convey that the row calculus is not just one calculus; it's a family of calculi, and I thought of a way to sort of a visual metaphor, visual approach to talk about the information that could lift people up to design level thinking without having to know a lot about the inner details, the algebraic details and the presentation and their relationship to type theory and theory of computation. As a part of the conversation, I invited Christian Williams to, hey Christian, you want to introduce yourself?
Thanks for having me on this. I have been recently hired as a researcher for RChain. Along with John Baez here at UC Riverside. We're working on the category theory aspects of RChain. Yeah, we're just really looking forward to it.
Cool. And part of the reason having Christian on the call is that this design level thinking is really fostered by a categorical gadget called a string diagram. And that will become clear as we go through this stuff. I know this is a podcast, but we've actually got some pictures that we'll make available, somewhere that we're driving here. The first picture is of a circuit that has effectively two inputs and one output. And that circuit, you just think of it as a little block. It's a logic block that requires two signals to come in before it can produce a signal out. Now, what goes on inside that logic block is just the pi calculus. And what it's doing is it's generating the stream of all processes, which are legal processes in the pi calculus. Now, in order to sort of generate that stream of all processes, there are two things we need that pi calculus does not provide. And one is a notion of the zero process. So you have to say what the stopped process is. The other is the notion of a name or a channel, also called a port. I use all of those terms synonymously. Part of the row calculus's critique of the pi calculus is that any real implementation of the pi calculus cannot provide an infinite supply of names that are atomic with an effective equality. That would mean that your equality is too smart to fit inside a computer, a finitary computer that we can build today. So we'd have to provide a notion of name that had some internal gadgetry, like strings have internal gadgetry, or numbers have internal gadgetry, or URIs have internally recognizable components. And as soon as you do that, then you're sneaking in a notion of computation.
So in practice, are they generating the names as natural numbers, and then they just import those? Or
yeah, different implementations do different things, right? Some implementations use some kind of De Bruijn indexing, or together with natural numbers, or strings. Various implementations use different approaches. But I think that the most important thing is that all of them share this characteristic that names have an internal structure. There are internal components to names. So even if pi calculus sort of says, well, all of those things are just messy details, if you want to have an effective theory, a theory that really helps out implementers, then you're going to need to articulate a theory of names. That's kind of the idea. And so one way to do that without importing some theory of names from the outside world is to modify our circuit. The picture of the circuit now has only one input. And so again, it's a box. There's one input, which is the zero. And then we tap the output for processes, and we feed it back into, we do a little feedback loop that goes back into names, but we make sure that before it's fed back in, it's not fed back in as a process, but it's sent through a little converter that converts processes into names. So you could think of that as the quote operation in the row calculus or row lang. And so we can see that this is well founded because at least you have a zero coming in. So you can feed the zero in, it goes out as a process that gets tapped and fed back in and quoted. And now we have a name, which is the quote of zero. And that can be used to generate more processes. And this is all visible directly from the diagram. You can see this in the string diagram. But the interesting point about this diagram is that now, this diagrammatic technique, in fact, is that now we can start to see that with this feedback loop, we have lots of other changes that we could ring. So, for example, since we know that the set of names, which I might call at P or at process, is isomorphic to the set of processes, then anything that I could represent or encode in names would be a reasonable name to import from the wild. So what we've done is we've kind of tamed the thing that people were doing in the first place, which was either using natural numbers or strings or URIs or any of these other technologies. We've tamed all of that by saying, well, in reality, our names come from quoted processes. But since quoted processes are rich enough to encode strings or natural numbers or anything like that, we can go ahead and import those in the raw, as it were, because we know if we needed to, we could get rid of them.
So even though these are being imported, they need to be expressible in the row calculus so that you can do an internal equality check of names.
That's right. Yeah, in the theory, that's the case. Now, notice that again, we can just use the imported notion of equality. So it's faster to compare two numbers on one of today's computers than it is to compare the equality of two row processes syntactically, right? But we know that we could, in principle, turn that calculation into the other one. And so it's safe to do. We haven't stepped out of the bounds of the computational model.
Mm-hmm.
And the same with strings, and the same with URIs and a bunch of other things. So what that looks like in the diagrammatic picture is now we have a box, and there's an input for the 0. There's also an input for these names that we've imported, which we'll just call n. And there's a little junction, right? Because we tap off of the output, which is labeled P. We feed that back in to the top, and at the same time, we also feed in the names. So now we have two different kinds of names, either an imported name or a quoted process. And this is starting to look a lot more like Row-Lang. And it's how we get from the pure row calculus to Row-Lang. And how we know that Row-Lang is safe, right? Because when we import these external names, we know that we haven't done anything, messy or fussy semantically. There's just we're just doing something that we could do in the pure row calculus, but because it's friendlier or nicer to human beings, we can go ahead and import these other kinds of names. And now the interesting thing is that we can employ this same technique on the other side, on the other set of inputs. So the only built-in input for the row calculus is the 0 process, the inert process, or the thing that's stopped. But again, because processes encode all Turing computable behavior, it's also safe to import other kinds of Turing computable behaviors, such as arithmetic. Right, so we could import the natural numbers together with arithmetic as built-in processes. So the diagram here is the original row diagram, and now we do the same kind of joining trick that we did before, but over on the 0 side of the inputs to the process box. So we have a little box that takes in two inputs. Those are the built-in processes and the 0, and then we feed those two streams as one stream down into the 0 input for the process circuit, and then we tap off of that. Yeah,
this is very practical because, I mean, in theory, you can do arithmetic in the lambda calculus or the pi calculus or the row calculus, but it's definitely a lot more involved than some simpler ways that we can do it now. And like you said, this is what Row-Lang has had in mind the whole time.
Yeah, that's exactly right. And and it's a funny thing because again, we had these intuitions from functional languages, right? The functional languages like Lisp or ML or OCaml or Haskell, right? They all intuit the idea that you could just swap in some built-in behavior for the lambda terms that would normally encode that. But to the best of my knowledge, no one has codified it in quite this way. Whereas here, it's very clear what it is we're doing, what the semantics are, and why it's safe.
Could you go into a little more detail about what you mean by safe here?
Yeah. So if someone presents us with some computational behavior, if we don't have a way, a crisp, clear way to encode it into the row calculus, then we're sort of left with a big question mark as to what the semantics are of including that feature in the language.
So when you draw these boxes, these junctions that are importing, that's an actual translation.
That's exactly right. Right. I mean, probably a more accurate way to say it is there's a refinement of this diagram down to the original Row-Lang diagram, where B gets boiled away.
I see.
That was a great question, actually. And now the interesting point is that we can combine both of these things, right? We can import built-in names and we can import built-in processes. And now we are effectively at a big chunk of how Rolang sits semantically with respect to the row calculus. The biggest difference between this new gadget and Rolang is that there are some additional control flow sugar or syntactic sugar that is added into Rolang, such as choice and join. We know how to do both of those as well, but that's kind of outside of the scope of this discussion.
Is that control flow coming from the combination of B and N?
No, the control flow is a separate thing. So choice is a separate encoding. You have to treat it slightly differently. The best way to do join is to start. That's really at the operational semantics level. So you modify the for to take in multiple inputs, and then you modify the com rule to allow for multiple outputs to hit those multiple inputs. Mm-hmm.
It's really impressive how well this idea lends itself to this visualization. I think that's going to help people a lot.
I hope so. I mean, I'm trying to enable this design level thinking, but also for people to understand like how much semantic terrain we can cover with just one framework. As you know, you and I were talking earlier, Christian, and I was saying, you know, when I began studying computer science, it was really sort of a much wilder field, and it was quite. And I think people have become inured or accustomed to, acclimatized to this idea that to go from just one idea to the next, you have to completely switch formalisms.
Yeah.
Right. So if people are used to going from regular expressions to context-free languages to finite automata with a couple of push-down stores, but in fact, those are all really, really different gadgets. And here we've expressed a range of computational characteristics with this essentially variations on a single gadget.
That's completely analogous to what's happened in math in the past 50 years or so, because all the different worlds of math were fairly separate, and then there were subjects that were kind of at intersections of certain subjects, but it was only recently that we finally internalized this broader perspective of viewing everything in terms of objects and morphisms and those higher relations.
Yeah, exactly. Right. This is kind of a very, very, very much inspired by that kind of trend. And to that end, you know, I mean, part of the reason I mentioned context-free languages and regular expressions is because there are interesting computational phenomena that are less expressive than Turing complete. And regular expressions, it's really hard to sit at a Unix terminal and make your way around without regular expressions. Likewise, it's really hard to navigate input streams in a program without regular expressions. They're very, very useful. Similarly, for any kind of language-based computational phenomena, it's really hard to navigate the world without context-free languages. And though they're a significant tool, and parsers and parser generators are a significant part of programming today. My feeling is that you'd want to be able to smoothly capture all of those capabilities as well. It turns out that you can do a similar kind of thing in the row calculus. If we imagine the original row calculus diagram, so we have our box with a zero input, and then we tap off of the output where we generate processes, and before we allow a process to be fed back in quoted form to be a name, we check it for a property. Property that we're checking is a syntactic form of the process. So, for example, we might check to see we only allow names that are output forms, or we only allow names that are for comprehension forms, or we have a finite set of names that we're allowing, and either the process is in that finite set or isn't.
So
these are the kinds of filters that we would employ. Go ahead.
For example, how could you filter for a syntactic notion that's more complicated, such as give me only a context-free grammar subcalculus of the row calculus? How would that work?
The big trick between context-free and regular is paren balancing. Any subset of the row forms that allow for regular plus paren balancing, and you can kind of see how you might do paren balancing by matching inputs and outputs.
Sorry, what do you mean by that balancing?
Parenthesis balancing. So being able to check that an S expression is well formed. So every open has a corresponding close. So you can kind of see how every open has a corresponding close corresponds to a discipline on the fors and the outputs. It's a neat trick, and you can apply this filter to that, and that gives you a subcalculus of the row calculus that has this restricted expressive power. And again, it's all within this single framework.
What's an example of a time when you want to make one of these restrictions? Just like a simple example.
Let's say that you want to reason about a subcalculus that is context-free. That to me is a really good one. So you're interested in that because you know how to do parser generators. Another example would be that's really important, especially for the future of Rolang, has to do with providing a total functional sublanguage. So a lot of times what you'd like to do is you'd like to compute a value rather than evolve to a new behavior. And I think a lot of programmers are more comfortable and familiar with this idea of computing a value, which is exactly why Rolang 1.0 is the shape that it's in.
I just realized this serves as a bridge to most programmers that are not used to this kind of thinking, and this filtering would be precisely the bridge that you can start with a subcalculus that you're more familiar with and then kind of expand.
That's exactly right. That's exactly right.
That's cool.
Yeah. So so one subcalculus is a total functional language. So which means it's not just that it's a confluent, right? So the non-determinism doesn't really matter in terms of the value, but it's also terminating. So there are, for example, the well-typed system F expressions is a total functional language. Okay, so we came in at Turing complete, and then we looked at some things that are less expressive than Turing complete. Well, we can actually consider things that are above Turing complete, and I know that maybe some people will be shocked or surprised by the idea that computation could be beyond Turing complete. But it turns out that real number computation, like if actually dealing with the actual real numbers and not some computable fragment or subset, is clearly greater than Turing complete. And in fact, there's a whole tower of expressiveness that goes out beyond Turing complete, and it's an infinite tower where you have, for example, the real numbers can be considered as oracles to Turing machines that answer certain questions that are beyond Turing complete. And then just in the same way that you have these hierarchies of cardinalities, you have these hierarchies of ordinals or of oracles that provide answers that some machine at that strata cannot answer. Now we can give a similar kind of thing, and let me just start with a simple example. You can imagine that there are names that are not reachable by the row grammar. So in particular, these are all names that are fixed points. So for example, if you write down the recursive equation, x is equal to the quote, so the at sign of output on 0 x. That's going to be 0 bang open paren 0 bang open paren ad infinitum. We can represent that kind of gadget as in terms of lazy calculations. You could write down, or in Haskell or any number of languages that provide a lazy computation, which allows to capture fixed points like that. And then you could extend Rolang to have the usual quoted processes as names and that name. it turns out that if you have that grammar, then there are names that are unreachable by that grammar, and you could close up by adding additional fixed points. And in fact, the limit of that process is having a fixed point operator on the definition of names.
Are you having to explicitly list out which of these recursive processes you're going to be adding, or is there a way that you can add? Are you saying that you can add all fixed points of the room?
Typically, you write there's a notation for fixed points called mu. All the mu legal expressions.
Yeah.
So mu x dot p, where x is a name that is bindable in p, and then you take the at of that. So you now say that names in this calculus are either quoted processes or these mu x processes.
So this
and that gives you the n. Exactly. That gets all the finitely generatable infinitary ones.
Yeah.
There's still more beyond those, but we can write those down. And then so that the diagram for this includes a little box for the fixed point that feeds into your name gadgets, right? So you have the tap off of the output P that feeds into your little combiner, along with another diagram that's generating these fixed points that feeds into the N. It's a lot easier just to look at than for me to explain in English. Maybe we'll make sure that the diagrams are available for people who want to take a look.
Yeah.
Now, there's a point that I made before, which is just that these infinitary gadgets are very much like roots of numbers. It's very much like Galois theory. So this kind of extension is almost in perfect analogy with the idea of taking a field and extending it with a root. And when we extend the field with the root, that root is like a name that is one of these fixed point gadgets. That turns out to be a powerful metaphor for how to think about not just the row calculus, but also going back to the pi calculus. You can do a semantic interpretation of the new operator in terms of one of these roots.
This has to do with thinking of recursive data structures as polynomials.
Yes.
Is the community like familiar and comfortable with that idea, or is that I assume that was a part of the class?
I did not cover that in the class, but it is certainly, it's well known in the programming language semantics area. I don't think that the programming language semantics folks have connected this idea of roots to this, but people in the RChain community are certainly familiar with this idea of an unforgeable name. Mm-hmm. And these roots are very, very much like unforgeable names. Once we've kind of opened the door to these fixed points or, infinitary structures, there's no reason why we can't just add in all kinds of crazy oracles, right? So any constructible number, so any number you can get to with a compass and straight edge, is reachable by one of these field extension, a sequence of field extensions via roots.
Oh, wow.
Yeah, so that's a theorem from way back. But there are numbers like the transcendental numbers, which are simply not reachable in this fashion, like pi and e and things like that. So we could imagine that we can throw in names that are like pi and e, just so that we have a sense of how numerous the transcendentals are, right? If you throw away the rational numbers from the reals, you'd never miss them. If you wound the real numbers around on a dartboard and you had a dart that was infinitely precise, always hit a number, and you threw that, and you're guaranteed that whenever you threw the dart, it hit the dartboard, and you threw the dart infinitely many times, you'd never hit a rational number.
Yeah. So with something like E, do you think that corresponds to a certain canonical process that's important for some reason?
Oh, for sure E is, right? Because it's related to the derivative, and so it's definitely related to a canonical process. That's interesting. Because we can certainly define a notion of derivative on processes, and we can we can ask for the fixed points in the derivative, and then E would be in some sense a notion of the quotation of that process. But I'm just talking more about from the point of view of expressivity and computability, one of the things that's really cool is that we can now just feed into our calculus these other crazy, wild names that throw in information that's just simply not reachable by the normal notions of computation. They become, again, oracles that computation can consult. And so we get this stratification. So we have one framework that gives us less than Turing complete, and greater than Turing complete. And we don't just have to do this on names. We can also do this on built-in processes, right? So we can now include oracles that do all kinds of crazy stuff for us. Even before we go out into the outer stratosphere of of computation, there's still all kinds of fun things we can do inside Turing complete. An example is the red-black calculus. Now, this is another technique that I believe, I've never seen anyone else contemplated, and it can be used in lots of different domains. I'll give an example in the row calculus, and then sort of point out that you could apply it to set theory as well. You can take the diagram that we built for the row calculus that had additional built-in processes, and you can make two copies of that diagram. So imagine you've got a red copy of that circuit, and you've got a black copy of that circuit. And you tap off of the red process output, and you feed it into the built-in port for the black processes. And likewise, you tap off of the black process port, where we're generating, the stream of processes coming from the black diagram, and feed that into the red built-in port. And so now they're kind of mutually recursive. You have two calculi that are mutually recursive on each other. One way to think about this is that it represents a kind of resource sharing capability. So a red process could run to zero and terminate, or it runs down to, it gets to a point where it's a black process. And at that point, you swap over into black processing. You can run that down to a zero, or to a red process, and then you're back into the red processing. A way to think about that is you've got one chip, one resource that is being, and you've got a yield operation between two different entities that are utilizing that singular resource. So the yield operation corresponds to switching back and forth between red and black.
This is such a good idea. I mean, this is building in the resource awareness at the most basic level.
It's cool. I mean, to me, it's a lot of fun because, one of the things that's interesting is that you could encode this back down into the row calculus. And the way to do that is because the collection of names is infinite. You can have two infinite subsets. So you can bifurcate the namespace, and then you can impose a discipline on processes that only use one namespace or the other. And so you could completely encode this red-black calculus into a discipline on using the names. But that turns out to be messy, right? It's hard for a programmer to get the name discipline right, but it's very easy for them to just use one keyword, yield. And so you could take this sort of higher level clean language that has this yield keyword and compile it down into this more sophisticated namespace management stuff, right? And so that's the real value or one of the values of the red-black calculus.
These diagrams really start to expand thinking about what's possible. And so I guess somebody's initial reaction to seeing the diagrams might be, well, how is that actually implemented? So is it completely summarized in the grammar generators for the row processes right next to them?
Yes, that's right. So on the diagrams that I created, what goes inside the boxes is summarized in the algebra. So what we're trying to do is to kind of show that there's a box and wire way of thinking, and there's an algebraic way of thinking, and that they fit together in a certain way. And in some ways, it's kind of like the difference between algebra and geometry, right? If you have an algebraic geometry, you can go back and forth between those two different ways of thinking. Yeah.
That's what the string diagrams are all about.
That's precisely right. So I'm not sure exactly which category would be best to interpret these string diagrams. I mean, it's pretty clearly symmetric monoidal, but apart from that,
Yeah. Yes, some very non-trivial feedbacks.
Yeah, that's right. Yeah, so being able to do feedback is you have to think about which categories to interpret the feedback. But I feel like there's enough evidence, as you know, like the final picture. I kind of summarize all the diagrams that were explored, so that people can get a sense of the variety of calculi, right? So we start from the pi calculus and we go all the way out to the red black calculus. I feel like this gives us a sense of the kind of features we would want in our in the category that would interpret these string diagrams, but also helps people see how this can organize our thinking when we're thinking about language features. It gives us a kind of architectural playground.
Yeah.
Yeah.
This is some really amazing stuff.
Well, thank you. That's very kind of you to say. Yeah, I just want people to be able to, see that there's more there than just the row calculus. It's a lot more than that, and we've barely scratched the surface. And this is what sits at the heart of our chain. This sort of little engine of creativity is right at the heart of our chain. So.
Yes. When I see them all together like that, one of the things I wonder is if two people are using different calculi that are similar. Obviously, this framework gives a way implicitly in which they're related. So how do you get two different calculi to communicate?
Oh man, I'm so glad you asked that question. I wish we had like a whole other hour session. Our hour's almost up, but here's what I can say. So Milner and Eifer and some other students went after a thing called bigraphs, in which they were trying to create a semantic framework in which they could put calculi side by side and compare them. I spoke with Robin at the time that he was doing bigraphs, and he said it was some of the hardest mathematics he'd ever done in his life. And I think a lot of people recognize that the bigraphical framework is challenging, let's say. It's not as easy conceptually as the pi calculus. And for good reason, right? There's more going on because he wants to be able to account for ambient calculi and lambda calculus and a bunch of stuff within a single framework. At least with the row calculus framework, I have a very crisp way of talking about the thing that you're trying to capture when you talk about a morphism from one thing to another. And before I go there, let me just quickly motivate. Why would you want to do this? Why would you want to sort of situate two calculi next to each other?
Yeah.
It turns out, 2003, Jan Gray, Alan Brown, Satnam Singh, and I all we worked together and built a pi calculus chip. And then Satnam, genius that he was, and we realized the chip on an FPGA. And then Satnam realized that the chip was so tiny, he could tile the surface of an FPGA with this chip. And now you suddenly have this problem of how to assign work to each of the chips. And it occurred to me that you could do a tree-like structure in which the leaves are these pi calculus chips, and the interior nodes are ambient calculi, which are all about shunting the work off to the right regions, which will ultimately get down to leaves which are doing pi calculus-like computations. Now you literally have this hardware realized combination of ambient and pi. And now, in order to reason about the correctness of the behavior of this this thing, which is doing pi calculus at scale with a giant workload, you want to be able to reason about both ambient and pi in the same thing. That is a strong motivation, in my opinion, for the kind of work that Robin was doing, whether or not bigraphs is the right way to do it.
Is ambient calculus a subcalculus of the row calculus?
You can do an encoding, but it's not a subcalculus. They're very different beasts.
Yeah.
At least if you restrict yourself to families of row calculi, you can talk about the COM rule in a new way. So you can imagine that when you do the reduction, so when a for comprehension meets an output, the output communicates the process Q into all the locations where the bound variable is. It communicates the quotation of Q into all of those. Now, instead of communicating Q, we could wrap Q up in a context K. And what this represents is a mediation between an environment and it allows you to talk about scale, right? A lot of biological phenomena, we've all heard about the butterfly wings and the hurricanes, but that metaphor is actually real in the cell, right? So the kind of temporal scale that happens in the cytoplasm is like femtosecond. It's really, really fast. Whereas what's happening in the genetic machinery, when the DNA is read and proteins are produced, that's happening like in the second level or even minute level. And so you have this vast scale difference. And you could imagine that accounting for that is done in terms of this context thing. So maybe what I'll do is say it's a great idea to stop there and leave this as a tantalizing unfinished that we do at another Brain Candy podcast.